Let's talk about single optic devices, and I want to emphasize single so as not to be confused with devices that have more than one optic, such as a telescope or a microscope. We'll talk about those in a later unit. Right now, we're focused on single optic devices, such as a magnifying glass. The basic idea is you have something you're looking at with the optic, so we'll refer to that as the object. And then you've got the optic itself. Now, what I've drawn here is a lens. I'm doing that just because it's easier for the purposes of my diagram, but realize that an optic can be a lens or a mirror. This is our general term for both of them. And let me just also say the difference between a lens and a mirror: mirrors reflect, so the light bounces off of them. Lenses refract, so that means the light actually passes through them. It changes medium. So it goes, in this case, the light would be in air, then it goes through, let's say it's a glass lens, so then it's passing through glass, and then it goes from glass to air again. So it actually refracts twice. But again, refraction is when it passes through, that means it changes mediums. Anyway, so you got the object, got the optic, and then the image. Now the distance from the object to the optic, that's known as the object distance. The distance from the optic to the image is known as the image distance. And these fit a very simple formula. We call it the optic formula. 1 over f equals 1 over do plus 1 over di. F is the focal length. That's an inherent property of the optic. It can only change if the curvature changes. So if the curvature of your optic changes, then the focal length changes. It is possible for really exotic, I guess you would say, optics, that the material could change, especially if you're talking about a lens. For example, if you've got a lens that's filled with water and then it froze, it would change from water to ice. That would change the focal length. But aside from something kind of unusual like that happening, you're only going to change the focal length if you change the curvature. The other important formula that I need to mention here with regards to this whole setup for a single optic device is for magnification. And that's the image height over the object height. This is basically just, we say image height, but really we're just comparing the size of the image to the size of the object. That's what we're doing. That's how we determine the magnification. Now, the main purpose of this video is I want to go over the terminology and the convention. There's actually a fair amount of new terminology that needs to be introduced, and convention. What I mean by convention is, when are some of these quantities positive? When are they negative? How can you tell? So that's what we need to discuss. And our starting point is going to be the two different types of images that can be created. There are two different types. There are real images and there are virtual images. Okay. Now, what is a real image? A real image is an image that can be projected at onto something. So it exists at a single point, or at some point in space, I should say. So when you go to the movie theater, the movie is projected onto the screen. That's a real image. Okay, there's a projector in the back. It's got a lens in it, and that is used to project the image onto the screen, and that's where that's a real image. It's right there to point in space. The projector in a classroom that I use, and I'm sure many other instructors use as well, that puts a real image on the screen. So these are images that exist at a specific point in space. Virtual images, they do not exist anywhere. You only see a virtual image if you look into the optic that is creating it. So for example, your bathroom mirror. When you look at yourself in the bathroom mirror, you only see your reflection if you look into the bathroom mirror. That image of you doesn't exist anywhere in space. Okay, it's not like you're standing there in the bathroom and magically an image of you appears on the other side of the wall to freak anybody out that's over there. That's not how it works. Okay? It's a virtual image. You can only see it by looking into the optic that's creating it. So the first thing about real images and virtual images, the difference between them. For real images, because they actually exist at a point in space, they have a positive image distance. Virtual images have a negative image distance. Additionally, real images are inverted. You might say upside down. More specifically, this means that compared to the object, the image has been rotated 180 degrees. This here, as I drew it, this would be a real image. That's why I drew it upside down. Okay. Virtual images are upright. Now, because real images are inverted, we say that their image height is negative. That's the convention there. And virtual images, because they're upright, we say their image height is positive. Now, looking at the formula for magnification, the object height, basically by definition, is always positive. And I should mention the object distance is always going to be positive for a single optic device as well. Okay. But anyway, the object height, always positive. So if the image height is positive, then the magnification is positive. If the image height is negative, the magnification is negative. So here, the image height is negative, so guess what? That means the magnification is negative. And here, the magnification is positive. Now, for real images, these can only be created by converging optics. Now, what is a converging optic? The converging optics, when light passes through them, the tendency is for the optic to bring the light together. So if you think about a magnifying glass, maybe at some point you used it to bring all the light rays from the sun into a point to burn a leaf or some grass or an ant or a younger sibling. Okay, it brings the light together. It's a converging optic. Virtual images can be created by diverging optics or converging optics. So a converging optic is going to bring the light together. That's going to be its tendency. A diverging optic, it tends to spread the light apart. Now, I've talked a little bit about magnification here. I want to add one thing that you can't put into either column as a general sense. And that just has to do with what magnification tells us. I should have mentioned this before when I was talking about the formula. But anyway, if the absolute value of the magnification is less than 1, then we call this a diminished image. Diminished. That means that the image is smaller than the object. Now notice I put the absolute value because it doesn't matter if it's inverted or upright. If the magnitude is less than 1. And on the other hand, if the magnitude is greater than 1, then we say it's magnified. I should have mentioned that sooner, but I definitely wanted to mention that here. Okay, so I want to get back to my list. I've got virtual images, I've got real images. Another listing that I find very beneficial to do is with regards to the optics. And that's going to be converging and diverging. So converging optics, these can create real or virtual images. So a magnifying glass, you can use that to create real images or virtual images. It'll create both. Okay? But a diverging optic can only make virtual. can only make virtual images. Another big thing about converging and diverging. Converging optics, the convention is that they have positive focal lengths, whereas for diverging optics, negative focal lengths. Now for converging optics, if we're talking about a lens, oops, that's going to be a convex lens. That's what I was drawing before, so it looks like this. If it's diverging, that's going to be a concave lens. And so that would look something like this. Now, I've drawn an example of a convex lens and a concave lens. The thing that really defines them has to do with, you look at how thick they are at the center and at the edges. If it's thicker at the center than it is at the edges, it's convex. If it's thinner in the center than at the edges, then it's concave. If we're talking about mirrors, a converging mirror, this would be a concave mirror. And so that would look like that. Where this is the light comes in and it bounces off. For diverging, that's going to be a convex mirror. Your car more than likely has a convex mirror on the passenger side. It says objects in the mirror may be closer than they appear. That's because that mirror is slightly, oops, ever so slightly convex. It's bulging outward just a little. I feel like I could have made this one bulge outward a little bit more. There we go. That's bulging outward just a little, and that makes it convex. So that mirror that's on the passenger side, that is a diverging mirror. Okay, so this is the terminology. Like I said, there's a fair amount. I think it helps to have these lists. I think this helps to clear things up. Some it helps to keep things straight. You do need to know this terminology. You need to be comfortable with it. You need to know the convention. And there's these formulas here that I've mentioned. I'm going to talk more about how these formulas work in a different video, but for this one I just wanted to focus again on the terminology and the convention.